All right, so now let's talk a little bit more about the mechanisms of these radical reactions, or the electron pushing arrows that we're going to draw from these radical reactions. Just like we saw before, they'll all sort of follow similar patterns. We can sort of categorize them. One note, another kind of nice thing about radicals compared to carbonyl cations is you don't have to worry about any rearrangements, right? So no methyl shifts or hydride shifts will occur with radicals, right? So in this example here, we would have had to have worried about the fact that there would have been a methyl shift to form the more stable carbocation. We're not going to see any such thing with radicals. They're stuck, kind of. All right, so let's talk about these different patterns. There's these 6 different patterns that we're going to see over and over again in our radical mechanisms. And again, by mechanisms, I'm talking about those electron pushing arrows. So the first one we've sort of already gone over, and that is the homolytic cleavage of a bond. And that is, remember, homolytic meaning that the bond breaks evenly. So I'm going to get my bunny ears where one electron is jumping onto one of those atoms and the other one onto the other. And again, that will form 2 new radicals, okay? What we're going to see over and over again is on our arrows are either going to be the uppercase delta, the triangle, or HV. So that is meaning it's catalyzed by either heat, that's what the delta means, or HV means light, okay? So, and light is a very common way to catalyze these reactions. You put in some high energy photons and that will homolytically cleave the bond, especially, and we're going to see this, especially in something like chlorine gas or liquid bromine. Those bonds can be homolytically cleaved by sending in a certain frequency of light. Okay. All right, so now addition. So what do we mean by addition? Right, so what we would have seen before when we had an addition reaction is some sort of an electrophile, and that electrophile was going to be attacked by that bond, by that pi bond. The pi bond was playing the role of the nucleophile and attacking that electrophile. Okay, here, when we have radical reactions, we don't have the same roles of nucleophile and electrophile anymore, okay? And most importantly is we can't have this bond being broken heterolytically like it is in this example here, right, with my 2-headed arrow. What's gonna happen instead is you're gonna have a new bond that's formed. It's still an addition, so you're still having a new bond that's formed between a carbon and whatever your radical is. But again, it's going to have to be heterolytic. So one of those electrons will come from the halogen and the other electron will come from that pi bond. Okay, but of course a pi bond has 2 electrons. So what happens to the other one? It jumps up and forms another radical on the other end. Okay, so this is a radical addition here. Notice how we have a radical on this side and a radical on this side. They're just in different positions, okay? All right, hydrogen abstraction as well as halogen abstraction. These are basically the same thing, mechanistically the same, except for what's being removed in a hydrogen abstraction is a hydrogen atom, and what's being removed in a halogen abstraction is a halogen atom, okay? Again, how does it look to form bonds with our new fishhook arrows? You got to have one electron coming from one species and another electron coming from another species in ears fashion, forming this bond here, right? So one electron originates at that radical, and then the other electron comes from what would currently be this hydrogen carbon bond. What happens to the other electron in that bond? Well, it's going to jump onto that other species. So again, you see these bunny ear kind of patterns. And so this would create a new, this is the abstraction part. You removed that hydrogen and you also have a radical. So again, this is another example of a reaction where you have a radical on one side and a radical on the other side. Again, the halogen is the exact same thing. The only difference is what's being abstracted. In this case, it's the halogen atom, and that bond's going to break heterolytically. Sorry, that's wrong. Homolytically, and I'll be left with, again, a radical on this side after starting on this side. Okay. The next one is the opposite of the addition for number 2. It is an elimination that you see with a radical. Okay. So let's see like what the answer looks like and see if we can't get there logically as to what's happening here. So it's elimination, right? So you're going to get rid of one of these substituents, a leaving group, and you're going to be left with a double bond. How does that pi bond form homolytically? Well, this radical will come down, form one part, and then the bond, my carbon-halogen bond, would supply the other electron. The second electron in that carbon-halogen bond would jump up and form that halogen radical. Okay, so this is now the opposite of the addition, the radical addition. This is a radical elimination. And again, note I have a radical on this side and on this side. All right, now the last one is called coupling, and it's really the reverse of a heterolytic cleavage. It's when two radicals find one another and form a new covalent bond, okay? One radical supplies one electron, the other radical supplies the other electron, and what you're left with at the end is just a normal old covalent bond, okay? So what we're gonna see is these radical reactions, they happen. They continue to propagate because you have steps like this where one radical's consumed, but another one is generated. And then finally, they get to the point where one radical finds another radical, and that stops things because it takes the radicals out, those highly reactive. And that would be the coupling step. So again, just to point out, and actually, I hate this table includes this bottom one here because it's not really of the same vein. But this is just pointing out how heterolytic cleavage is just the opposite of coupling, right? So a heterolytic cleavage is when this bond breaks heterolytically so that this electron jumps up here and this electron jumps up here. Well, the reverse of that would just be that coupling where this electron comes down here to form this bond and that one same thing, right? So my fish hooks, this was got kind of messy. Let me make this prettier. So this comes and forms a new bond, and then this comes and forms that new bond, right? So homolytic cleavage and coupling are just the opposites of one another. And same thing with the addition to the pi bond. Radical addition and radical elimination are just opposites, right? So in the radical addition, this electron comes down. I break my pi bond in this heterolytic way. This electron is going to form that new bond. And then what happens to the other one? It jumps on to that other carbon. Okay, likewise, we could do the same thing in reverse or the elimination. So now this one's going to come down, form a new bond. The other electron for that bond is going to be supplied by this bond here. And then I'm going to form a radical on that species. Okay. So these 6 different patterns can get categorized, like 6 different electron pushing patterns, right? The different arrows can be categorized into 3 different categories. The first one is initiation. Okay, so this is the step in the reaction where you go from no radicals to 2 radicals. Okay, so you start out with something that isn't a radical and then you generate these radicals. That's the initiation, because again, these are the highly reactive species that are going to like kick this thing off and start this reaction to go. So the next step is propagation. Okay, and these are any of these 4 categories of electron pushing arrows would be considered a propagation, whether it's the addition to the pi bond, radical addition, or radical elimination, halogen abstraction or hydrogen abstraction. These are all propagation steps. And the easiest way to tell a propagation step is because you start with a radical and you end with a radical, right? So again, new bonds are being formed, but you still have this propagation of the radical species. It's just who's bearing that radical electron is changing. But if you start with the radical in one step and end in another step, that's a propagation. All right, and then finally, the whole thing ends when you get to the termination step, or this was what we would call the coupling, which is when two radicals find one another and form a covalent bond, right? And again, this can be seen because you got our pattern can be obvious to spot because you got two radicals to start with and no radicals to begin with, or to end with rather. And so this signifies like the end of that particular radical reaction, right? Because you've got these two highly reactive species that find one another and then create this nice stable covalent bond. Okay, so of those 6 different patterns, we can categorize them into these 3 different steps, whether it be initiation, propagation, or termination.